A scanning electron microscope is a type of electron microscope that produces images of a sample by scanning the surface with a focused beam of electrons. The electrons interact with atoms in the sample, producing various signals that contain information about the surface topography and composition of the sample. The electron beam is scanned in a raster scan pattern, and the position of the beam is combined with the intensity of the detected signal to produce an image. In the most common SEM mode, secondary electrons emitted by atoms excited by the electron beam are detected using a secondary electron detector called Everhard-Thornley detector. The number of secondary electrons that can be detected, and thus the signal intensity, depends, among other things, on specimen topography. Some SEMs can achieve resolutions better than 1 nanometer. Specimens are observed in high vacuum in a conventional SEM, or in low vacuum or wet conditions in a variable pressure or environmental SEM, and at a wide range of cryogenic or elevated temperatures with specialized instruments. Principles and capacities. The signals used by a SEM to produce an image result from interactions of the electron beam with atoms at various depths within the sample. Various types of signals are produced including secondary electrons or SE, reflected or backscattered electrons called BSE, characteristic X-rays and light cathodoluminescence or CL, absorbed current or specimen current and transmitted electrons. Secondary electron detectors are standard equipment in all SEMs, but it is rare for a single machine to have detectors for all other possible signals. Secondary electrons have very low energies on the order of 50 electron volt, which limits their mean free path in solid matter. Consequently, secondary electrons can only escape from the top few nanometers of the surface of a sample. The signal from secondary electrons tends to be highly localized at the point of impact of the primary electron beam, making it possible to collect images of the sample surface with a resolution of below 1 nanometer. Backscattered electrons are beam electrons that are reflected from the sample by elastic scattering. Since they have much higher energy than secondary electron, they emerge from deeper locations within the specimen and, consequently, the resolution of backscattered electron images is less than secondary electron images. However, backscattered electrons are often used in analytical SEM, along with the spectra made from the characteristic X-rays, because the intensity of the backscattered electron signal is strongly related to the atomic number of the specimen. Backscattered electrons images can provide information about the distribution, but not the identity, of different elements in the sample. Characteristic X-rays are emitted when the electron beam removes an inner shell electron from the sample, causing a higher energy electron to fill the shell and release energy. The energy or wavelength of these characteristic X-rays can be measured by energy dispersive X-ray spectroscopy or wavelength dispersive X-ray spectroscopy and used to identify and measure the abundance of elements in the sample and map their distribution. Due to the very narrow electron beam, some micrographs have a large depth of field yielding a characteristic three-dimensional appearance useful for understanding the surface structure of a sample. A wide range of magnifications is possible, from about 10 times to more than 500,000 times, and about 250 times the magnification limit of the best light microscopes, scanning process and image formation. In a typical SEM, an electron beam is thermionically emitted from an electron gun fitted with a tungsten filament cathode. Tungsten is normally used in thermionic electron guns because it has the highest melting point and lowest vapor pressure of all metals, thereby allowing it to be electrically heated for electron emission, and because of its low cost. Other types of electron emitters include lanthanum hexaboride Lab6 cathodes, which can be used in a standard tungsten filament SEM if the vacuum system is upgraded, or field emission guns, which may be of the cold cathode type using tungsten single crystal emitters, or the thermally assisted Schottky type, that use emitters of tungsten single crystals coated in zirconium oxide. The electron beam, which typically has an energy ranging from 0.2 keV to 40 keV, is focused by 1 or 2 condenser lenses to a spot about 0.4 nanometer to 5 nanometer in diameter. The beam passes through pairs of scanning coils or pairs of deflector plates in the electron column, typically in the final lens, which deflect the beam in the X and Y axes so that it scans in a raster fashion over a rectangular area of the sample surface. When the primary electron beam interacts with the sample, the electrons lose energy by repeated random scattering and absorption within a teardrop-shaped volume of the specimen known as the interaction volume, which extends from less than 100 nanometer to approximately 5 micrometer into the surface. The size of the interaction volume depends on the electron's landing energy, the atomic number of the specimen and the specimen's density. The energy exchange between the electron beam and the sample results in the reflection of high-energy electrons by elastic scattering, emission of secondary electrons by inelastic scattering, and the emission of electromagnetic radiation, each of which can be detected by specialized detectors. The beam current absorbed by the specimen can also be detected and used to create images of the distribution of specimen current. Electronic amplifiers of various types are used to amplify the signals, which are displayed as variations in brightness on a computer monitor. Each pixel of computer video memory is synchronized with the position of the beam on the specimen in the microscope, and the resulting image is, therefore, a distribution map of the intensity of the signal being emitted from the scanned area of the specimen.